So as I said, we covered double linked list and simple linked list. So for today, I want to show you and implement together a special linked list. And we will focus on a simple linked list because you have seen the overhead last week. And we have discussed when a double linked list is useful. And we all agree that if you need to go back and forth inside the list, yes, then you need a double linked list. But we can still have pretty fast simple linked list if we allow us to go in reverse, but not like in reverse going from head to from tail to head, but like getting to the tail. And even yesterday, when we had the meeting about the assignment, one of your colleagues was trying to implement the solution like this for the assignment, because if you read the specs, is a little bit about performance. So by doing those benchmarks, maybe you will see a real difference when you play with arrays and lists. So he had a similar approach. And yes, in reality, we use a lot simple linked lists, but we know they have this issue with when we want to insert at the end, and that's a queue. Okay, we know we have a stack or versus queue as a simple linked list, and if you want to insert at the end, it's costly because we need to traverse the entire simple linked list in order to reach the end. And in order to speed this, because yeah, a simple linked list has more advantages of an array. We covered that 2 weeks ago. We can increase dynamically its size. That's the thing which convinces us that we need to use that in some cases, a simple linked list. But it has this disadvantage of the complexity of traversing a simple linked list. You need to go through all the nodes. So why not patch this problem of a simple linked list in order to improve its speed regarding inserting at the end? So it will be like a queue implementation, but with an improved speed regarding insertion at the end. And in the same time, because we didn't cover that, for today we will also discuss how to remove items from a list, how to delete them. Okay, so let's define the data structures for today. Okay, and after that I will ask you if you want to I don't know, include something else in today's example. So we play with standard library .h. Okay, we play with standard input. Okay, for printf, scanf, and also malloc. And I think a string for strings. Last week we talked about a server that it may be overwhelmed by the number of messages. And in that case, in order to search for messages with the highest priority or for the client with the highest ID, we implemented a double linked list that in the end will allow us to go back and forth inside that collection. So let's choose the same structure again, but I will just simplify it, because the simple linked list that has 2 pointers, one pointing to the head and one to the tail, it's actually sometimes called a ring buffer. Okay, so it's like a circular list, but instead of pointing from the last item to the first one, and there's no advantage here, we will manage the 2 starting and ending points of the list, the head and the last item. Okay, so by having those 2 references, we can control at any time the head and the tail. Okay, so in that case, it's like you have a ring, because at any moment you can access with the same complexity either the tail or either the head. And generally, this is called a ring buffer because this is like a queue of messages which are processed in round robin. Round robin means there is no priority, is like the first message here, the first message processed. So they are all equal. The only thing that matters is their order. So because the server is overwhelmed, we want to speed up the adding of a new message in the queue of messages that they wait to be processed. You know, the server is overwhelmed. Why to traverse a list with 1 million elements in order to add a new message? Because even that will take a lot. So we want to help the server, okay? So by implementing a ring buffer or a simple linked list or a circular simple linked list, in this way, the server can take with complexity 1 the next message to be processed in line, and we will simulate this. And also in the same time, we can add with the same complexity new messages inside that queue. Okay, so that's the idea for today. It's a simple linked list which has a much more improved performance for inserting at the end. Okay, so once again, the messages are like this. So I don't know, it's a chat window or something. Let's say 100 charts. Okay, and we have client ID. Okay, and that's it. Because here, remember, we don't have any priority. It's all about processing the messages as they arrive in a queue, which is faster than a normal queue because we have the pointers to the head of the simple linked list and also to the tail. So the node of that simple linked list looks like a normal node. Okay, node. So we have the message, and we have the pointer to the next node. Node next. So it's a simple linked list, but what's different is this. Okay, and let's call this one, this structure, messages ring buffer. Okay, so we benefit from the advantages of a simple linked list, which means we can increase the size with any number of elements dynamically. Okay, so we are efficient in using memory. Okay, and secondly, we benefit from the fact that we remove items from the head, and this is a stack. So a stack will always remove values from the head. And in the same time, we benefit from the advantages of a queue by inserting new elements at the end. Okay, so this is quite it's quite a queue. Okay, because new elements are added at the end, and all the elements are removed from the beginning. Okay, it's like a queue at the, I don't know, desk or something. Okay, so what do we need? We need the node. Once again, let's pass a name for this structure. Char asterisk, I don't know, buffer name. Okay, and after that we need the node for head and the node for tail. And remember, we need to initialize them. Okay, and also this one, just not to forget. Okay, so these are the structures that we will use. This is the container for the message, and this is the container of a node. Okay, and this is the structure that we will use. So we need to manage two pointers, one at the beginning and one at the end of the data structure. Okay, so we will cover insert and remove. Insertion is clear, it's always at the end. Remove is from the head. And yeah, we will need to cover the particular case when the ring buffer will be completely deleted because it will we will remove all messages. So it's clear what's the example for today. Okay, so it's a simple linked list, and we will manage head and tail of it. Okay, so at any moment, if something is not clear, please say something or ask. Okay, so once again, let's start with dummy main, just to be able to build. Let's suppose you have a list of 1 million nodes, okay? And you have the head. Now, if you want to insert a new element, how many steps do you need to take in order to reach the end of that list of 1 million nodes? So you see, the major drawback of a list, always compare the list with arrays, with the simple vector, because vectors have limited size. Vectors have complexity 1 in order to access any element inside that vector, okay? So they are the fastest data structures that exist. You can instantly access any element inside the array. The problem with the vector or array is that it has a limited size. If you want to add a new element, you need to recreate, you know the story, okay? So a simple linked list has been invented just to cover this problem of an array, because a simple linked list can grow with any issue, with any numbers of new elements. You just add a new one in memory, link that to the previous one, and that's it. Now, the problem with simple linked list, so it solves the problem that vectors have. This is dynamic size, let's say. But the problem is that simple linked lists are not perfect. They have the issue that if you want to reach the end, you need to go through all the nodes. So you see, you solve one issue, but you generate another one. And this is actually the entire problem with data structures. You don't have a perfect one. Each is trying to fix a problem of another data structure, but it's in the same time generating new ones. So that's why, in order to fix this problem with a simple linked list, meaning that inserting at the end, you need to go through all the nodes, we bring this new, it's not a different simple linked list. It's still a simple linked list, but we manage it differently by managing head and tail, okay?
Okay.
Any other issues regarding this example? So can we go on? Okay. So let's try to build this. Let's see if we have any syntax errors here. Okay, so everything looks okay. The structures are defined okay. So once again, you have seen the approach of the other examples. We will go by writing small functions that we will reuse. So the first thing that I want to do is to create a function that will create a message. Okay, so we have a function that let's say init message. We need a constant char text and client ID. Okay, we create the message here, message, and we init the data. It's a static field string copy. So string copy message text, text, and message client ID equals client ID. Okay, and we return the new message, return message. So in this way, we have a function that will create messages. We have another, we need another method to cover creation of nodes. Okay, and we talked this several times. Always the new nodes will be in heap. So in order to give you a response, I will give you its address, but the node will be in heap. Okay, so init node, and for that we need a message, and that's it, to create a node. So node, new node equals, we use malloc, node malloc of size of. Okay, and now we need, we had a mistake last week here. So we need enough space for a node, not a message, which means next and a message. Okay, so here will be size of node. Okay, we got it. Now let's copy the values. The first thing that I want to check is the next, that should be null. And because here we don't have dynamic fields, I can copy the message with equals, because remember, equals, it's always doing copy paste. So if you write this, it will copy paste the entire structure, which means the array of 100 chars and the integer. So it's okay. So once again here, works because does not contain pointers. Now, if the message had some pointers, then it should be tricky. Sometimes works, sometimes not, depending on what you do with these messages. If you delete them, then you'll create a dangling pointer. So when you have pointers, it's safer to create your own space and copy the values there. Okay, but in this case, we can do it like this. So we know how to create a new message. We know how to create a node. And let's create a function that will create a new message ring buffer. Okay, and because this is just a structure that is, sorry, this one, it's managing different stuff. Let's return message ring buffer.
Shouldn't we return the
Yeah,
node?
yeah. We actually must return new node. Thank you for that. Okay, and here we init a ring buffer. Okay, init ring buffer. In order to create it, let's define one message ring buffer mrb, or just buffer. It's just a buffer. Don't forget to init your, even if they're initialized there, it's better to be safer. So it's not a pointer, it's just a structure. So head equals null. And when we init this, I think we need its name. Okay, so const char name. And it's like this. Okay, it's a constant pointer to a char. So buffer head equals null, buffer tail equals null. Okay, and the name, it's a dynamic field, so we need to create some space for that. So buffer name equals, not new char malloc of string length of name plus 1. You know why? Because we need the backslash 0, and this should be multiplied with size of char, but we know it's 1. Okay, and string copy buffer name and name. Okay, and return the buffer. Okay, so in this way we covered the creation of all these articles. We don't need to worry later. We just have functions for that. Now the other function that we will need in order to check if everything works is a way of printing the data. So maybe I want to see what's inside this buffer. So I want to print the entire list to see which messages are there. Okay, so let's do a function for printing a message. Once again, I'm trying to write small functions that will handle only one thing. So in this way, let's say we reduce the risk of doing mistakes, even for simple stuff. Because if you try to do a lot of simple things in a single function, you have a complexity, because you have multiple things to worry, to think how you should do that and that. So in this way, you can do even trivial mistakes for stuff that you know, because your mind, you type, but your mind will be like 5 minutes in the future. So it's like, how, okay, and I know how to print the list, but how I will do that. So in that moment, you'll be distracted and you'll do a mistake. So that's why try to do things in steps, okay? So print message, and we need a message, message, okay? And here just a simple printf will go like this, from client %d and the message. Maybe that could be a stock exchange, okay? And now stocks are overwhelmed with, if you read the news, sometimes they close the stock exchange for 15 minutes because it was overwhelmed by all these fluctuations and all the things that's happening, and it's influencing the stock market. So that could be a server for a stock exchange, and all these are buy and sell orders, okay? And yes, in that case, the server will be overwhelmed. So you need a queue. Okay, so from client, and that will be the message. So it's the message client ID, message text. Okay, so this is printing a message. And the last method, print buffer, print buffer. Okay, so we need a message ring buffer, and we want to print it. Okay, now what we want to do is to print the buffer and its content. So the first thing that I want to do, and sometimes you forget to initialize, or you initialize pointers to null, but when you try to use them, sometimes it's easy to forget to check them. And if you try to print something which is managed by a null pointer, you'll have an instant runtime exception. So in this case, if you see here, we have a name. So before jumping and printing the name, why not manage it like we manage the head? You know, always we check the head, because if it's null, we will have a runtime exception. So why not check this pointer also? So let's check this one. If buffer name different than null, then we print its name, print \n, let's say %s content. Okay, something like this. Okay, else printf. And else, we don't have a name, it's an empty anonymous ring buffer. Okay, we can, let's say, printf just a ring buffer.
You forgot to say buffer name in the printf.
Ah, yeah. Buffer name. Okay. And here just a buffer, a ring buffer. So in this way, we checked if we have a name there. Maybe someone didn't initialize that pointer. So always check your pointers, because sometimes they can be null, and you will have a runtime exception because you can't print that the values at that address. So we want to print it as a normal simple linked list. And remember, because it's a simple linked list, even if we have the pointer to the tail, we can't go backwards. Okay, so even if you know where the tail is, you can't move backwards because we don't have a previous pointer. Okay. Yes, a circular list, but a double one, a double linked one. Because in that case, for each node, you have prev and next. So the head of a double linked list will also have a previous, which is actually pointing to the last node. But if you have a simple linked list, which is a circular simple linked list, it's like this one here. Actually, a circular simple linked list is not so helpful, because when you end at the end, you can move fast to the head, but this is also something you can achieve easily because you have the head. So there is no advantage here. So for a circular list, when you say a circular list, it should be a double linked list. But once again, you have all that overhead of all the links, okay? And at some point, it's easy to mess them up, okay? So you have the increased complexity. Okay, so here, we don't have a circular list. There is only one way to traverse it, which is like from head to tail. Okay, let's always start with corner cases, let's say with particular cases. And one easy corner case is when you don't have a list. Okay, that's the easiest one. So if buffer head equals null, it's empty. Okay, we don't need to do anything else. Okay, it's empty. With this, we solve the issue. Now, if we do this, and I want to avoid the else, like I said, exit the function if you reach a dead end, okay? Because otherwise you can mess things up with if else, if else, if else, and so on. Okay, why worrying? Just exit. Just here a ring buffer. Okay, so we covered the current case. Now, if head is different than null, it means we have at least one node, and that's sufficient to traverse the list. We can use a for or a while loop. Which one do you want? How do you want to traverse?
While.
While. Okay. In order to traverse it with a while, let's define a temporary pointer. Okay. Let's call it it equals with or p, whatever. You can choose your own variable names. So it's equal with buffer dot head. We know head is not null. Why? Because we are here. Okay, because otherwise we are out already of this function. We start with the buffer head. So while
it un next diferit de null.
Yeah, but you see when you write this while it next diferit de null, this while will exit when this pointer is pointing a node that exists but has a next reference null. So this is a precondition loop, which means if you reach the last node, this is the last node, right? It has the next null. It means it will exit. So it will not print it, because here we want to print the node. So this while will exit before printing when you are on the last node. And we want to print the last node, right?
Okay.
So
we can actually do a do while in this case if you want to
yes,
maintain
if you
the
want,
same while.
yeah, if you exactly. So if you want to keep this it next different than null, then you need to do a do while, because you'll have a post conditional loop. The exit condition will be checked after the body of the loop is executed.
Or we can copy the body of the while after we exit the while.
Yeah, but in that case, you need to do a copy paste.
Okay, so CTS, don't repeat yourself.
Exactly, and having the same instruction twice, maybe you have a bug there, and you will realize later you will fix one location, another bug, and yeah, you know how that will end. So we want to exit when
but we cannot use it next dot next just to check if there is something after that, so that we won't finish the while yet.
Like this?
Yeah.
So let me paint you something. I will share the paint. Do you see the paint window?
Yep.
Okay. So let's see. We have this list. Okay, these are all nodes. Okay, something like this. And now I will draw the links between them. So this is the first one. It's pointing here. this is pointing here, this is pointing here, this is pointing here, this is pointing here, and this is pointing here. Okay, now this is the head. Okay, this is head. So we start with it here. It is starting here. Sorry, it. Okay. So at the beginning, it is pointing to the head. Let's switch back to our code. So we start here, okay? We start here, we are at the head because of this, okay, buffer head. So let's see, while it next different than null behaves like this. First, it will check if this is true, and after that, it will do this. So do this after condition check. We are all agree, right? This is how while is behaving. It will check this, and after that is doing this. And here we want to print the node. Okay, so it is here. Let's change the color. Now, if I number the nodes, this is 1, 2, 3, 4, 5, 6, and 7. When you say next, it next, and at the beginning you are at the head, which node is that? It next.
3.
It's 3. So you see, we are here. We want to print each node. This
I
one.
got it.
You got it, right? And we are
Yeah.
checking the third one. So when do you think we will exit? Based on the condition, is like when next is null. So I think that we will exit while when we will be actually here on 5. Why? Or not on 6, because
we
6
will be checking the next after 7.
Exactly. So we will exit the while when we are here. So we will not print even 6, and 7 has 0 chances to be printed, right?
Yes, I got it.
Okay, so it's obvious it's not next. Now, while it next, when it will stop, let's go through on the image. So we are here. Is next different than null? Yes, we will print 1. Move to the next one. Is next of 2, which is 3, different than null? Yes, we will print 2.
6.
4, 5, 6. We are here. Is next of 6 different than null? Yes, it is. We will print 6. Move to the next one, and now while it's checking the condition. Is your next different than null? No. Is null, we exit while. So which node we don't print now?
The last one.
The last one.
So we can print the tail?
Yes, or you see, while it's checking the condition before doing something here. So what do you think it will happen if I write this? While it different than null, let's see. We are here. Is it different than null? Yes. Print 1. Move to the next. Is this different than null? Yes. We reach this point. Is it different than null? Yes. Print it. It will become next, null. Now, while it's checking, are you different than null? No, I'm null. So it will exit. So is not this a better approach?
Okay.
Now, if you like and your colleagues already said that, this will be the equivalent. Do while it next different than null. So you see, if you want to check always next different than null, this is the way you should write it, because the do while is different, because we'll do this and after we'll check the condition. So you will have the chance to be here on 7 And after that, you will exit, because while we'll verify when you are on 7, hey, what's your next? It's null. Okay, we will exit. Okay? So these two are equivalent if you want to write them either like this or like this. Okay, so let's print the current node. We have a function for that, which is print message of it message. Okay, and it equals it next. Okay, and obviously you should do the same thing here, but I will comment them because it will print the same stuff again twice. Okay, and I need to initialize that. Okay, so this is the alternative. So now we know how to print the ring buffer. Okay, we print its name, we check if we have something here, and after that we print its content. Okay, let's see if this works, because at this point we can actually test stuff. Let's create a message ring buffer. Yeah, buffer, let's call it buffer, equals init, sorry, init ring buffer. So let's say we are buying stocks, and this is, let's say, Apple Stock Exchange. Okay, so we buy stocks for Apple. Okay, we create it, let's print it. Even if it's empty, we should see some messages. Buffer. So build, rebuild. Yeah, this is my issue with my personal issue with Visual Studio, so don't worry. Now, if you don't have any compiler errors, you should see a message like an empty ring buffer. So I need to define here, define CRT secure no warnings. Okay, build, rebuild. Okay, everything looks okay. So let's run this. Control F5. So Apple Stock Exchange content, it's empty. Okay, we have no buy or sell orders. Okay. Okay, so let's implement the two methods that will complete this example, which is add a new message and remove a message. So we add always at the end because we have the tail, and we always get a message or process a message by removing it from the head. Okay, so this is like a queue. Okay, first in, first out, a FIFO. Okay, so let's define the insert message. Okay, insert message. Okay, now for a queue, common verbs are add and get, if you want to get something, and you know, for a stack is push or pop. Okay, so let's use the same thing. Insert generally means insert in different locations. Okay, so add message. Okay, what do we need in order to add a new message to the ring buffer? What do we need?
A message.
The message, exactly.
And the ring buffer.
Exactly, and the ring buffer. So let's start with it. So here I have the message ring buffer, and do we need to return something? No. Okay, and now the question, remember, always ask yourself this: is any of these variables going to change here by any of their attributes? So let's see, do we need to change the message inside add message?
No.
No. So yes, I see the answer on chat. Okay. And yeah, the pointer, but which pointer? So do we need to change the message ring buffer? Let's see. The name will not change. Okay, we don't want to do that. Is the head going to change when we add a new message?
No,
So if
the tail will gonna change.
exactly, but what will happen if you have an empty message ring buffer like we have now? The first message that you will insert will be what? The head and the tail, right?
Yeah.
So is the head going to change? Yes, not all the time, only once, but because that will
we
happen.
must put a condition. It's one node in the list.
Yeah, but if it's an empty list, then it will change, because if you insert something in an empty list, the head is already null. So the new node is actually the head and the tail. So the head will change.
Okay.
Yeah. And is the tail going to change? Yes, more than head. Actually, without the exception, when I think there is no exception, the tail will always change. Why? Because even if you have an empty message ring buffer, the new node will be the head and the tail. So the 2 pointers will change. And after that moment, the tail will always change. Okay, so because of this, we know we need to pass the variable by pointer. Okay, because of this question, is going to something inside this structure to change? And if the answer is yes, it doesn't matter if it's only once or 2 times. If it's yes, you need to pass it as a pointer. Okay, so let's cover the special cases. Okay, so let's cover the simple one. The list is empty case. How do we know it's an empty list? If buffer, sorry, head equals null, it's clear it's empty. Why? Now you can also check the tail. If we manage it correctly, we don't need to worry about the tail if the head is not. So in this case, now in any case, we create a new node. This should be the first thing that we should do. Check this thing that we need to do. Have you created a new node? So because we don't need to insert, let's say, unique messages, it means any message that we receive will be a new node in the list. So let's create it. Node, new message, new node, equals init node of message. Okay, so we just have it. Next is null. We know that because of init. So you see, we don't need to worry. That's why this is the advantage of writing small functions and reusing them. So you just cover one step without worrying about what we need to do next. Now let's move to the next. Always approach the easy stuff at the beginning, and after that dive into the complex part. So we cover this special case. The list is already empty. We know it's empty because the head is null. So in this case, the new head is the new node equals new node, and buffer tail equals new node. Okay, so for a particular moment in time, this ring buffer is a circular list because it has only one node. It's like you can go round and round forever. So we covered that. Return. Okay, so we just added the new node, is the only one, don't need to worry. Now, if we are here, like I said, if you don't like this approach, you can write an else here, open brackets again. You can do it differently. Okay, now if we are here, it means we have at least one node. But at this moment, we don't care because inserting at the end means only one thing. So insert at the end. We don't need to traverse the list. This is the benefit of having the tail. This is where we gain time. over a normal simple linked list. Okay, so we just need to do this. Buffer, sorry. Yeah, it's okay. Buffer tail next equals new node. So we just linked the new node to the tail. Now it's linked with the other nodes. And buffer tail equals new node. Okay. So that's all. Okay. We just inserted the node at the end. If you don't have this link, simple linked list with tail and head, you need to traverse the list like we did when printing it, and you stop on the tail and you do this this part. Okay. Okay, now let's see if this works. Okay, so now we have the power to add messages inside the list. Let's see if this works. So let's buy and sell something, some stock. So let's create some messages. Message buy one equals, I think initially you had the text and after that the ID. So it's like buy 1000 and client ID is 1001. Okay. So buy two, let's say this is another client, and sell one. Okay. Sell 550. Okay, let's add this these messages. So I have add message where into the buffer buy one, control D, buy two and sell one. Okay, and let's print it. Print bring buffer. Okay, build rebuild, control F5. Initially it was empty. Now from client 1000 buy sell, so everything looks okay. If anyone has any issues, questions, if you have problems, compiler errors, you can share the screen, just tell me and we can all look and help. Okay, so if anyone needs help. So the order of the messages should be the order of adding them. Okay, so they are in the same order we added them inside the buffer. This is the property of a queue. For a stack, you will see them, if you print the stack, it's like seeing them in reverse because it's LIFO, last in, first out. Okay, for a stack, it will be in reverse. Okay, so if anyone, if everybody, it's okay, let's do the other action, like processing nodes. So this is get message. So here we want to get a message in order to process it. And when you say get or pop, it will always means remove it from the queue. Okay, it's like you don't need to keep it there, you get it and you process it. Okay, so in order to do that, we need a function which is called get message. Okay, so the other one was add message. Now, what do we need as input arguments for get?
The buffer.
The buffer.
And the node or message.
Yeah, but if you know the message, why are you asking me for it? You know it, right?
Yeah.
So why are you calling get message when you already have the message? You know? So yeah, but it's always the first. It's like a queue.
Ah, da, sorry.
Okay, so
Yes,
that's
yes.
why we don't need the message. Okay, we clarify this. It's a queue.
Yes.
Okay, so we need only the buffer. Now, by any chance, when you remove a node from the buffer, is any chance that the head or tail will change?
Yes.
Yeah.
Yeah, the head will always change. You see, this is the opposite of the get of add. When you remove something from a queue, the head will always change. And when you reach the last one and you remove even that one, then is the one moment when the tail is going to change. So there are a lot of reasons to pass the buffer as a pointer, because the head and the tail will change a lot. Now, what do you need to get from get message?
A node.
A message.
The message. You see, this is like transport container. You are interested only on the package and not on the van. You don't need the van, okay? Maybe sometimes you may need the van, but they will not give it that to you. So when you ask something from a collection, generally you don't ask for the container, for the transport mode. You ask for the content. And in that case, is the message. So I'm not interested in how they store the message. For me as a server, I need only the message. I can process the message, which is the buy or sell action and the client ID. That's it. I don't know what's a node for me. So this is transparent for me. I don't care. So always focused on the content. Okay. So we will always return the message of the node. Okay. Once again, start with the easy part. What's the easiest situation when I'm asking you to give me something from the queue?
It's
The
empty.
queue is empty.
The queue is empty. Okay, let's check this. If buffer head equals to null, now the queue is empty and I need to return something. So we need to make a convention. I can't return null, for example. So I need to pass you a message. So in this case, we make this convention, and this is something the server will know because this is our protocol. This is a protocol. It's a set of rules that all parties are using in order to communicate. So in this case, we create a message and we set the message client ID equals -1. Okay, and in the same time, why not use the init? It's much more okay. Init message. So let's say empty message, or we can also write something here like no action, but we say this. So for us, this is the way to tell the server that we have no messages for you. Okay, so because it's mandatory to return something. Okay, so this means no messages. No messages. And the server will know that. Okay, we cover when the list is empty. The other case, let's see, it's any difference if the list has only one node versus a list has many nodes? I think it is, because if the list has only one node, by removing that node, the list becomes empty, right? So how do we check if the list has only one node?
If head equals tail.
Exactly, because they are pointing to the same unique node. So if head equals with buffer tail, okay, they are not null. We covered that. So because if the head is null, we are already out of this function. When we reach this if and these two are equal, it means they are not null. Okay, they couldn't be at this point. So at this point, we have only one node, only one message left. Okay, let's take it. Message equals buffer head or tail is the same message. Once again, we don't have dynamic fields. Otherwise, it's better to create a function like copy message. So in that copy message, you will, it's like the copy constructor at object-oriented programming. Otherwise, the equals will at some point do some harm. But in this case, it's a static structure. It doesn't have any dynamic fields, so it's okay. Equals the bit by bit copy will work. Okay, we copy it. Now let's release the nodes. So we have it here. Let's release the nodes, because otherwise we can create memory leaks by leaving nodes in heap. So let's release them. How do we do that? The opposite of malloc is free. Newer worked with delete. So free what? Free buffer head or tail is the same, because they are pointing to the same node. Now, if you try to do free buffer tail, then you will shoot your foot again. So try not to do that. You'll generate a runtime exception. You can't release, you know, the problems. Can't release the same space again. You don't own it after the first free. So, and because they are pointing to the same address, once is sufficient. Okay, and now mark the buffer, because now it has become an empty buffer. So how we do that? Buffer head equals buffer tail equals null. We initialize both pointers with null and return message. So in this way, the ring buffer will become an empty one. It had only one node. We know for sure because of this. And the last scenario is, let's say, the complex one. You have multiple nodes. So we know we don't have only one node. We have at least two because of this. So this is the at least two messages left. Okay. So we remove the node from the head, which means what? The head will point to the next one, and we delete the current node, which was the previous head. So let's take the message. Sorry?
Trebuie să creăm alt nod acum, ca să întâi mutăm pe următorul nod și după îl ștergem, nu?
Yeah. Because if we do this free, we lose the node and we lose the next. If you do buffer head equals buffer head next, you lose the current node, so you can't free it anymore. It's like, okay, what was the chicken or the egg? What was the first? So yeah, we need a pointer to have a grasp on the current head. After that, we change the head to the next one. And by using this temporary pointer, now I can release it. So node P, or let's say current head equals with buffer head. Okay. And now we can move the head. It's safe to move it. Equals with buffer head next. Okay, we still have the pointer to the previous node. We can take the message from it. Current head message. And now we can free it. Free. Now it's not the current head, it's the previous head. But yeah, a bad choice of names here. And now return message. So in this way, we move the next to the head to the next one, and we return the message. Let's test this. Build, rebuild. Okay. Let's process some messages. So message M1 equals get message from address of buffer. Okay, let's process it. And in order to process it, I will do here. Let's do a printf here. Printf, sorry. Printf. \n processing messages. Okay, let's print it. Print message M1. Let's get another one. This can go like this because it's the same message again and again. M equals get message at buffer. Once again, print it. M. And now let's check the ring buffer. Just to be sure that this works. Okay, so we had 2 buy orders and a sell one. We processed the buy orders and now we print the buffer again. Control F5. So processing messages buy. There are the first 2 messages here. And we have another one, which is the sell one. So where are you? Okay, but where? Yeah, I'm talking with your colleagues on chat. So what do you want to see? Do you want to see the get message here? Okay. Now, if you have, until your colleagues are finishing implementing, if you have questions, so that will be a simple linked list that has 2 pointers. Now, if you ask yourself, should we do an insert method in the middle? It doesn't make any sense for this kind of list. So you are not using it for the proper option if you try to insert in the middle. Okay, the idea is to insert at the end and get from the head. So in this way, you gain speed. Yeah, you want to ask something? Yeah, it's a queue, but it's a more performant queue than a queue which you manage only by its head.